All right, students, welcome to Chapter 8. So this is all about normal distribution and probabilities. And really, this is going to be a good foundation and good stepping point about inferential statistics. Last week, we learned about hypotheses, specifically the null and research hypotheses. And Chapter 8 really allows us to start looking at the probabilities of there being differences or probabilities of there being significant relationships between groups or between variables. So objectives for Chapter 8 are to know the properties of the normal distribution and why it's important in the real world, know how to calculate z-scores, which is a type of normal distribution, and determine the proportion of scores that are greater than or equal to, less than or equal to a given z-score, or to determine the proportion of scores that are between two z-scores. We'll also learn the empirical rule and how it relates to z-scores and probabilities. And then we'll also know how z-scores, standard deviation, and the mean, raw scores, and percentiles, percentages all relate to each other on the normal distribution curve. So I want you to take a look at this first distribution here. We have about 1,000 individuals, and we can see that with 1,000 individuals, we have different frequencies, right? We can see we have three modes, specifically three modes, all with the same height, same frequency. But if we look at the overall distribution, we see that it's pretty much a normal distribution. But look at when we add 10 times the amount of people. Now we have 10,000 people. Notice we now have different distributions and different frequencies for different answers and responses. And so these two distributions so far will each have their own mean, their own median, and their own mode. But we can see that they're both normally distributed. The only difference is the number of people, our sample size. So if we added 10 times more, now we have 100,000 people. Look what's happening to our normal distribution. We're going to have a different mean, we're going to have a different median, we're going to have a different mode, all different measures of central tendency and dispersions, but yet our normal distribution curve is looking much more smooth and much more what we call normally distributed. And so as we increase our sample sizes from 1,000 to 10,000 to 100,000 to 1,000,000, we end up getting pretty much the entire population, right? The more people you have in your sample, we see our normal distribution becomes normally distributed, becomes a nearly perfect normal distribution where we have one mode, one mean, one median for the entire population. And so these four graphs really give you a nice visual and summary of the central limit theorem, which you may have learned in previous math classes. And briefly, what the central limit theorem is that with a very large sample size, and if all of those individual cases are independently and randomly picked from the entire population, you will have a normal distribution of those scores. And we can see with our 1,000,000 people sample size, we have a nice normal distribution. And so let's talk about this normal distribution. What are the properties of them? Well, one of them is the range, and it covers all possible values for any given variable. So underneath this curve is going to contain all possible variables, or all possible values. Normal distribution curve also has symmetry. So if you look at this curve, if you folded it in half, lengthwise, you'd have a nice mirror image that the curves will overlay on top of each other. And this is going to be a very important property that we'll think about and we'll see later. Unimodality. Really, we only have one mode, and that mode also equals the mean and the median. And the shape is a very distinct bell-shaped curve. And lastly, it is asymptomatic, whereas the tails never really touch the x-axis because it represents an indefinite chance of extreme scores. That no matter what, there is a small likelihood of an extreme score, of an outlier occurring. However, if they did touch, then that means that the extreme score is non-existent, that the there's going to be a finite amount of scores. So let's look at this a little bit closer in terms of visual inspection. Again, underneath this curve covers all possible scores. And we see that given wherever a score falls, and we can see that there is a corresponding percentage that falls underneath this score, or underneath this curve. We also see symmetry. So if you folded it down halfway down this middle, which is we see 0 and also the mean, that will have equal halves. And again, it's also unimodal. There's only one hump, one mode, and if we cut it down again, this is also the mean, and we see this is 0, and we'll talk about this later on when we talk about the normal distribution in z-scores. We also see the shape, again, bell-shaped. And notice underneath the bell shape that certain parts of the distribution have a fixed distance away from the mean. Again, the mean is going to be the mode, which is the median, right down the middle of the curve. And then asymptomatic. Notice again, this line never really touches the x-axis. So what kinds of variables have normal distributions? What do we mean by this, and what types of variables? Well, things in our daily life. So if you took the SATs, or if you've taken any type of standardized test, or if you're going to take the GRE for graduate school, really intelligence is normally distributed. We're going to have really, really smart people and not so really smart people, and then everywhere in between. Also, height and weight. These are normally distributed in nature. In the human population, we're going to have people that are very, very short, and we'll have people that are very, very tall, and most people are going to fall within a normal range, an average range. Just the same thing with weight. And even cholesterol. In cholesterol, this is going to be important in terms of how this is going to be applied to our real lives. And how we feel like, okay, well, how high is our cholesterol? Is my cholesterol too high or is it too low? And what does that mean in terms of health risk or health benefits? So think about these variables. Intelligence, scores on some standardized tests, height, weight, cholesterol levels. What level of measurement are these? Ungrouped interval ratio variables. And so ungrouped interval ratio variables are really the ones that I'm going to be working with when it comes to z-scores and normal distribution. So why is a normal distribution so important anyway? Well, I kind of alluded to this a little bit when I mentioned cholesterol. So let's think about your lab results. If you look at a typical lab result here, we see right in the middle, we have your results. And on the left, we see these are all for a thyroid test. We have free T3, free T4, TSH, and other types of biomarkers. And then notice we also have a reference range. And this reference range tells the doctors and tells you where do most people that are healthy fall. What is the reference range that says that most people who are healthy are going to fall somewhere between these two values? And we see for T3 levels, there's a reference range of 3 to 6.2 picomoles per liter. And we see that your results are 4.3. So you'd say, all right, well, I'm pretty healthy. No worries there. Same thing for your T4. You see your results are about 17.8, and the reference range falls between 12 to 22, so you're right in between, so again, you're healthy. But look at your TSH. Your results are 0.04, whereas the reference range says that most people who are healthy fall within 0.4 to 4, and you're way beyond that. You're actually 10 times lower than what the reference range should be. And look at your TGAB. You're way above the reference range, which should be less than 60 international units per milliliter. And so this reference range is based upon 95% of people who are healthy. Well, where did we get this number, and why 95%? Well, again, we want to know what is a good range that most people are. We know that people are going to have different levels of thyroid levels, of cholesterol, of different things in our bodies, yet we're all going to be normal. We're all healthy. But knowing that we all have different levels, we have to figure out, okay, well, if you are sick, what is going to be a range that indicates that you are sick, whether it's high or low levels? And so this is important in terms of looking at normal distribution. We know that most levels in the body, most things related to our body, we can measure to see if you're healthy, what are going to be the normal ranges. And this is where we have reference ranges for all sorts of different tests. And so we can see if you are inside or outside of this range, whether or not that's indicative of some health risk or some disease or illness. So take a look at this video. It's more of a conceptual problem where it addresses different types of variables in the world and kind of goes through the thought process of whether or not these things are normally distributed